Swayam Prabha. Digital India. Educated India.
So, last class I have discussed how we can model the pile as a finite beam, and then we can determine the deflection, slope, bending moment and shear force at different depth along the pile, and we assume that the horizontal modulus of subgrade reaction is uniform along the depth of the pile. Now, today's class I will discuss how we can model the pile as a semi infinite beam, because if the pile is short pile, then you have to go for finite beam, but if the pile is a long pile, then we can go for semi infinite beam, because the solution for semi infinite beam is easier compared to the finite beam. And before we go to the semi infinite beam part, so there is a small correction, and that correction is that this slope in that due to moment there will be lambda cube. Okay. So, this is lambda cube. So, that this is the correction. So, that you should do, and this is also the lambda cube. Okay. So, this is lambda cube. So, that is why when you take the m0, which is the moment due to the fixity of the pile head. So, that amount of moment will be developed in the pile due to application of the H due to the fixity of the pile in case of fixed headed pile to make the net slope at the fixed head 0, because for the fixed head boundary condition the slope should be 0. So, this is that is why we will get the m0 is this value. So, now we will go for the pile as a semi infinite beam. So, we will go for the pile and as I have already discussed that how we will get this k rho h to the k rho m different these values, coefficient values for with respect to different lambda L and z by L. Z is the at any depth, L is the length of the pile, and lambda I have already discussed. So, this is lambda L 2, this is 3, this is for 4, this is for 5. Now, we will go for the pile as a semi infinite beam. So, when the pile is called the long pile, so if the lambda L is greater than 2.5, then the pile can be called as a long pile where the length is where L is the length of the pile. So, at per Hetini, a beam is called the long beam is lambda L is greater than 3.14. As per VII, the beam is called moderately long beam if lambda L is greater than 2.25 and less than 5, and if the lambda L is equal to 5, the beam is called long beam. So, that means as per Hetini, because it is a Hetini's beam beam concept we are using. So, if it is less than 3.14, then we can go for a long pile. So, that means if lambda L value is greater than 3.14, then you can go for the pile with semi infinite beam, pile as a semi infinite beam. If the lambda L value is less than 3.14, then you can go for pile as a finite beam. So, and from this study I have observed that if lambda L is greater than 2.5, so more or less your semi infinite beam and the finite beam will give more or less same value. So, that means which I want to say that if the lambda L is less than 3.14 or the less than 2.5, so definitely you have to go for pile with finite beam. Okay? But if or pile as a finite beam, but if the lambda L value is greater than 3.14 or 2.5, then you can consider pile as semi infinite beam, or you can consider pile as a finite beam also. But if it is less than that, then definitely you have to go for pile as finite beam. But if you can see your finite beam case, this lambda L value is given up to 5. So, if it is greater than 5, so definitely you have to go for pile with semi infinite beam. So, that means what does it mean? That if the pile length is less than 3.14 or 2.5, then you can go for pile as finite beam. If it is 2.5 to 5, then you can either use finite beam or semi infinite beam. If it is greater than 5, then you have to use it as semi infinite beam. Okay, so, that semi infinite beam, the similar type of concept like finite beam we are using here. So, here semi infinite beam, that we are using that this is the h value, h is acting here. So, that means in such case this is for the free headed pile. The equations are similar way. Here also in two ends, or there is one end, you have to apply the end conditioning forces, okay, P0A and M0A. These end conditioning forces you have to apply. So, here your springs are in this direction. So, you can because this is the way we have to derive the equations. If you change the direction, your equation sign will also change. Okay, so, for this condition we are deriving these equations. So, we have to apply end conditioning forces, and this is infinite. Okay. So, this beam is infinite along the depth towards the depth. So, that means after solving this, we will get y is equal to 2h lambda kh d d lambda z, theta is equal to minus 2h lambda square by kh d into a lambda z, moment is equal to minus h by lambda b lambda z, and shear force is equal to minus h c lambda z. Similarly, for the moment, this is the infinite direction, and for the moment, and h is acting this direction. So, moment is acting this side. So, for the moment we can apply that this is for h and this is for m 0. The equations are y is equal to minus 2 m 0 lambda square by k h d c lambda z, theta is equal to 4 m 0 lambda cube divided by k h d d lambda z, and bending moment m is equal to m 0 a lambda z, and the shear force is minus 2 m 0 lambda b lambda z. So, where as you know that a lambda z is equal to e to the power minus lambda z cos lambda z plus sin lambda z, and z is this direction. Then b lambda z is e to the power minus lambda z sin lambda z, c lambda z is e to the power minus lambda z cos lambda z minus sin lambda z, and d lambda z is equal to e to the power minus lambda z e to the power minus lambda z cos lambda z. So, at z equal to 0, a lambda z equal to 1, B lambda z will be 0, C lambda z will be 1 and D lambda z will be 1. So, this is the equation. So, which is slightly easier than the beam equations for beam as finite length, because where I have given those coefficient as a tabular form, but here the coefficient equations is available. So, you can put directly the z value and you will get the deflection, shear force, bending moment and the slope at any point. Okay. So, now these equations are valid for free headed pile. So, again for fixed headed pile, so for the fixed headed pile how we can determine these values. So, I am writing here, this is for fixed headed pile. For fixed headed pile, okay. So, again the net slope at z equal to 0 will be 0. Okay. So, that slope will be due to the h and due to the m 0, and because this m 0 is the moment due to the fixity of the fixed end. So, net slope will be 0. So, we will equate this slope due to the h. So, that slope is minus again as I mentioned, we will not consider the sign, we will consider only the magnitude, because h and moment they are acting in opposite direction, which is the actually in that case only the net slope will be 0. So, that is why we will take only the magnitude. So, that magnitude if I take, so that will be 2 h lambda square k h d a lambda z, that will be equal to 4 m 0 lambda cube, then k h d into d lambda z. Okay. So, the m will be equal to m 0, the moment due to fixity, okay. So, that will be equal to h, this is by 2 lambda, this is lambda cube lambda square, and then a lambda z at z equal to 0 and d lambda z at z equal to 0, okay, at z equal to 0. So, as I mentioned, at z equal to 0, a lambda z is equal to 1, d lambda z equal to 1. So, it will cancel out. So, finally, the m 0, the moment due to fixity will be h divided by 2 lambda. Okay. So, this is the equation which is similar to the equation for finite beam. So, but here that k theta h at z equal to 0, k theta m at z equal to 0, that is also close to theta h. So, which is not 0 actually, theta h is not 0 at z equal to 0, this is z equal to 0. So, that is why you have to calculate or you have to put these values depending upon what is your lambda L. Okay. So, you can see as lambda L value increases, this theta h value is close to 0. Okay. So, this is 1.0003 for 40015, then 3004, then this is 0 h 1.13, for the 2 it is 1.13. So, that is why for other case, for more than 2, 3 it is close to 0, 1, then 4 is also close to 1, then 5 is also close to 1. So, that is why I want to say that if your lambda L's value is less than 2.5, so definitely you have to model your pile as finite beam. Okay. And if it is more than that, then you can model it as finite beam or the semi infinite beam. So, you will get more or less same value but it is up to 5. If it is more than 5, lambda L value is more than 5. So, definitely you have to go for pile as semi infinite beam. Okay. So, now let us solve one problem, that how we can use this concept that I have discussed. So, that means the example problem where it is constant H, K H value. So, it is constant K H or uniform K H. Okay. So, determine the deflection of a pile at ground surface. So, that means Z is equal to 0 if H horizontal force acting is 50 kilonewton and K H is 70 meganewton meter square per meter and EP IP is given 3700 kilonewton meter square. So, two cases, one is for free headed pile and another case is for fixed headed pile. So, first one we will consider that pile as let me check what is the L by D values are given. So, D value is given as a 0.75 meter and L is given 75 meter, sorry 7.5 meter. So, L is given 7.5 meter and your D is 0.75 meter. Here it is given 0.4 meter you should say. Okay. So, because this is the actual dimension, D is 0.4 meter and L is 7.5 meter. So, let us see which equation or which condition we should apply as a pile as a finite beam or pile as a semi infinite beam. So, for that first we have to calculate the lambda value. Okay. So, lambda is 4 root of K H D divided by 4 E P I P. So, this is equal to 4 root of K H is 17 to 10 to the power 3 in terms of kilonewton per meter square per meter. D is equal to 0.4 and 4 E P is 37,000. So, this is equal to 0.66 meter to the power 1. So, the lambda L value is 0.66 into 7.5. So, this is 4.95. So, which is close to 5. So, as I mentioned, if it is within 2.5 or 3.1425 or I should say the 2.5 to 5, then you can use it as a pile as semi infinite beam or pile as finite beam. Okay. But if it is greater than 5, then you have to go for a pile as a semi infinite beam, but it is here it is exactly 5. So, you will use both the concept, you will use pile as finite beam and pile as semi infinite beam, and let us see whether there will be any difference or not. So, first case that this is for free headed pile and first we are considering the pile as a finite beam. So, pile as finite beam, what is the equation? So, pile as finite beam so this is the equation, deflection is 2 h lambda K h d into K rho h and you have to determine at z equal to 0. So, this is 5 lambda L is equal to 5. So, this is the lambda L is equal to 5. So, at lambda L is equal to 5 Z L or Z equal to 0, k rho h is 1.003. So, this is 1.003. Okay. So, here we are calculating it for z equal to 0, but if we are using it for at any z. So, according to that value or that coefficient value you have to consider. Okay. So, according to that coefficient value you have to consider. So, here it is 1.003. So, now I will put this value, this is for free headed pile, y is equal to 2 h lambda by lambda k h d into k rho h, and rho h at z equal to 0, because we have to calculate that settlement as z equal to 0. We have calculated is 1.0003. So, we will get this is 2, this is 50 kilonewton, lambda is 0.66, kh is 17 to 10 to the power 3 into d is 0.4 into 1.003. So, this value is 2.36 millimeter. So, the deflection of the pile head for free headed pile is 2.36 millimeter. By considering this is beam as pile as finite beam. Okay. So, now next one we will calculate for fixed headed pile. The same condition, if the pile head is fixed, then how we will calculate that? Now, we will get the, we will calculate what will be the moment that will generate due to the fixity. So, moment due to fixity. So, that moment expression is given 2 by h by 2 lambda k theta h at z equal to 0 and k theta m at z equal to 0. Now, at k theta h as z equal to 0 for lambda equal to 5, lambda L equal to 5, this is 1.003 and this is 1.002. Okay, at z equal to 0. So, that we will put here. So, this is h is equal to 50, 2 lambda 0.66, this is 1.003, this is 1.002. Okay. So, that moment that will generate or develop due to the fixity is 37.9 kilonewton meter. Now, the next step is that if the pile is free, then there will be deformation of 2.36 millimeter or free headed pile. But now, pile is fixity and due to the fixity there will be a counter moment is developed and that value is 37.9 kilonewton per meter. So, now we have to calculate what would be the deformation for this moment which is developed due to the fixity. And if you subtract this moment, this deformation which is developed due to the fixity from the free headed pile deformation, then I will get the deformation for the fixed headed pile, because that much moment m0 moment is developed due to the fixity and that is acting in the opposite direction to the h. So, basically that is reducing the deformation of the pile head. So, definitely the deformation of the pile head under fixed head condition will be less than the deformation of the pile head under free head condition. So, that means this deformation reduction due to the moment which is generated due to the fixity of the pile head. So, first you will calculate what is the moment due to what is the deformation due to m0. So, that moment we have given the equation for the moment for this pile as finite beam, and that deformation is 2 m0 lambda square k h d into k rho m, and rho m at for phi lambda L equal to 5, rho m is this one. Okay. So, this is the minus 1.003. So, now we will put this value here. So, this is the equation is 2 m 0 k h d lambda square k rho m, and rho m is minus 1.003. So, will be 2 m 0 is 37.9 divided k h is 17 to 10 to the power 3, d is 0.4, this is minus 1.003. So, this value is 37.9. Oh, there is a lambda square also. So, if there is a lambda square, then I should write lambda square means 0.66 square into minus 1.003, okay, minus 1.003. So, this is 2 into 37.9, 0.66 square minus 1.003 from the table, then k h is 17 to 10 to the power 3, 0.4. So, this value is minus 1.18 millimeter. So, the net deflection, that will be deflection due to the free hand 2.36, and now the reduction of the deflection due to the moment which is developed due to the fixity. So, that is 1.18. So, the deflection of the fixed headed pile at z equal to 0 is 1.18 millimeter. So, this is the deflection of the pile at z equal to 0 for free headed pile, and this is the deflection at z equal to 0 for fixed headed pile. Okay. So, this can be done for any depth, remember that, but when you calculate m 0, this k theta h, k theta m will be always z equal to 0, remember that. Whether your z value can be anything, suppose you are doing it for z equal to 1 meter, but still you determine the m 0 considering k theta h, k theta m at z equal to 0. But when you calculate the other coefficient, that you can calculate for the required depth, okay, because the table is given z by L. So, that means if z equal to 1 and L equal to 7.5, it will be 1 divided by 7.5. You can determine for any depth, but this m 0 you have to determine at z equal to 0, remember that. So, this is the for if I consider pile is equal to finite beam. Now, if the next, if pile is as semi infinite beam, if pile as semi infinite beam. So, I will use the same problem, but here again for free headed pile, the equation of y is equal to 2 h lambda k h d into d lambda z. So, d lambda z, which is equal to 1 at z equal to 0, but for z equal to 0 it is 1, but for any other z I have discussed that how to calculate this coefficient for any depth or any distance. Okay. So, and that will be the you have to convert this, this is radian, delta z is in radian. If you multiply the delta with any z, so that will be radian, you have to convert it to degree when you use them to sine or with cos. Okay. So, remember that. So, that means here this is z equal to 1. So, I can put this is equal to 2, h is equal to 50, and lambda is again 0.66, because that will not change whether it is a semi infinite beam or finite beam. So, lambda value is 0.66, k h is 70 into 10 to the power 3, and d is equal to 0.4 and it is equal to 1. So, this will be 2.36 0.36, which is the same value that we obtain when you consider pile as a finite beam. So, because as I mentioned, if it is more than 2.5, then you will get more or less similar value. Now, if it is fixed pile, then the moment due to the fixity m0 is already been developed, that is h by 2 lambda. So, this is h divided by 2 lambda. So, h is 50, 2 lambda is 0.66. So, this is 37.9 kilonewton meter. So, the deflection due to m0 will be minus, because that deflection due to m is given minus 2 m0 lambda square k h d into c lambda z. So, that is 2 m0 lambda square divided by k h d into c lambda z, and this is c lambda z, yes, c lambda z, and c lambda z is equal to 1 at z equal to 0. So, this will be minus 2 into 37.9 into 0.66 square divided by 70 into 10 to the power 3 into 0.4 into 1, and that is equal to minus 1.18 millimeter. So, the net deflection will be 2.36 minus 1.18, that is 1.18 millimeter. So, we are getting the same value if we consider the pile as a semi infinite beam, or if we consider the pile as a finite beam, because here the lambda L value is 5. Okay. Now, you can check the same problem if the lambda L value is say 2, okay, and then you solve it with semi infinite beam and the finite beam. Then you will find there will be a difference between the deflection that you are getting for finite beam and the semi infinite beam. Okay, that you can check, because in that case you have the result that you are getting by considering beam as a finite pile as a finite beam, that is the proper result, because in that case you cannot model pile as semi infinite beam. Clear? So, but both the cases, whether it is pile is finite beam or the semi infinite beam, where kh is uniform. So, that means this concept is more or less useful for cohesive soil, where the kh value is uniform. Okay. So, in the next class I will discuss that how we can determine the settlement and the other quantities like bending moment, shear force and the slope for a pile if kh value is not uniform, it is varying with depth. So, that will be discussed in the next class. Thank you.